In physics, every now and then you come across these incredibly clever hacks that make problems that seem impossible suddenly easy. So today we're going to dive into one of the most elegant examples out there, a trick that, as we'll see, isn't really a trick at all. It's actually a window into a much, much deeper mathematical truth. All right, let's jump right in with what sounds like a simple enough question. Imagine you take a single electric charge, say a positive one, and you bring it near a big flat metal plate that's grounded. What does the electric field around that charge look like? Seems straightforward, right? Well, it turns out trying to calculate that field directly is a surprisingly tough nut to crack.
See, the real headache here is the plate itself. Because it's a conductor, the charges inside it can move around freely. So when you bring your positive charge close, it pulls all the negative charges in the metal right up to the surface. And now you don't just have one field from your one charge, you have this whole messy, complicated spread of induced charges on the plate, and every single one of them is creating its own field. It becomes a real nightmare to solve.
But what if there was a way to just ignore that messy plate completely and still get the exact right answer? Well, this is where the magic happens. It's a technique called the method of images, and honestly, it feels a little like cheating. The first step in this method is just pure genius in how bold it is. You just get rid of the conductor. Poof, erase it from the problem entirely. Now, I know that sounds completely wrong, but stick with me here, because this is the first step in a seriously powerful procedure. So how does it work? It's these three steps. First, like we said, you remove the plate. Then you do something totally imaginary. You place a second opposite charge, a virtual one, on the other side of where the plate was, exactly as if it were a reflection in a mirror. And finally, you just calculate the electric field from these two simple point charges. And the incredible part? This super simple setup gives you the exact correct answer for the electric field in the space where the plate used to be. It's amazing.
So to put a more formal name on it, this is the method of images. It's really just an elegant mathematical tool that helps us satisfy the physical rules of the problem. You see, there are rules, we call them boundary conditions, that say how the electric field has to behave. For instance, the voltage on that metal plate has to be 0. By cleverly placing this fake, imaginary charge, we've built a whole new, much simpler problem that just so happens to follow the exact same rules.
And this really gets to the core of the mystery, doesn't it? Even the textbooks admit that the whole thing feels somewhat artificial. I mean, why on earth should inventing a charge that isn't even real give you the correct physical answer? It works, we know it works, but it feels like some kind of mathematical sleight of hand. So this is the big question, right? Is it just a lucky coincidence, a mathematical fluke, or is there something way deeper going on under the hood? Well, to find the answer, we actually have to travel back in time and meet a forgotten genius whose work holds the key to it all. The real reason this trick works lies in the work of a man named George Green. He was a self-taught mathematician and physicist back in the 19th century, who was in so many ways light years ahead of his time. George Green is one of the great unsung heroes of physics. He was the first person to really develop the idea of electric potential, what we all call voltage today. But his most powerful invention, and the real key to our puzzle, is a mathematical tool that's now named after him, Green's functions. And these things are used absolutely everywhere in modern physics. But here's the tragic part. His genius was almost completely unrecognized while he was alive. He published his most important essay way back in 1828, but it was basically ignored. It was only after he died that his work was rediscovered and championed by the famous physicist Lord Kelvin, who immediately realized how revolutionary it was. You have to wonder, right? How could ideas that are so fundamental to physics just get overlooked? Well, it turns out it was kind of a perfect storm of factors that kept his brilliant work hidden away from the mainstream scientific world. The crucial thing to understand is that Green was just operating on a totally different level than most of his colleagues. He was deep into these highly abstract mathematical ideas at a time when most scientists were focused on more practical, hands-on experiments. Put simply, he was just way, way too far ahead of his time. So let's get into the core concept he developed, because this is what explains why the method of images isn't a trick at all. It all boils down to this incredibly powerful idea of a response to an impulse. Okay, so the key idea is called a Green's function. Now don't let the name scare you. It sounds super technical and complicated, but the concept behind it is actually incredibly intuitive. It's beautiful, really. I want you to picture this. Imagine a perfectly still pond. Now you drop one single tiny pebble right in the middle. It creates that classic ripple that spreads outward, right?
That specific, predictable ripple pattern, that is the fundamental response of the pond to one tiny disturbance at one single point.
And this is where the power comes in. Because once you know the shape of the ripple from that one single pebble, you can figure out the complex, messy pattern from throwing in a whole handful of pebbles. You just add up all the individual ripples from each pebble, and you get the final combined pattern. And that is exactly what a Green's function is. It's the basic building block. In our electricity problem, the pebble is a single point of charge, and the ripple is the electric potential it creates. The Green's function tells you what the potential looks like from one single point charge, and once you have that, you can build up the solution for any arrangement of charges you can dream of.
So how does this all connect back to our magic mirror trick? Well, the method of images is really just the tip of the iceberg. It's a very specific, very elegant application of this much deeper, much more powerful idea of Green's functions. The trick is the shortcut. The Green's function is the fundamental reason why that shortcut even exists.
All right, let's bring it all home now. It's time to connect the dots between George Green's deep mathematical insight and that clever mirror trick we started this whole thing with.
And here it is. The big reveal. The method of images isn't a hack at all. It is a brilliant way of building the correct Green's function, the correct fundamental response for our specific problem with the metal plate. The combination of our real charge and that fake image charge together creates a potential that behaves exactly the way the true potential has to behave at the surface of that plate. That image charge is simply the mathematical tool we need to construct the real physical answer.
And just to put a final point on how mind-blowingly ahead of the curve George Green was, his intuitive physical idea of a response to a single impulse was so advanced that it took over 100 years for mathematics to even catch up. The formal language needed to properly describe what he'd figured out, something called the theory of distributions, wasn't developed until the 1950s.
And that really brings us to our final thought. The method of images starts out looking like an artificial, clever trick. But when you dig just a little deeper, you find this profound, universal principle about how physical systems work. And it really makes you wonder, doesn't it? How many other clever shortcuts that we use in science and math are actually just the tip of an iceberg, pointing the way to a much deeper, more beautiful, and more fundamental reality?